Hello everybody. Good morning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm seeing 31 of you right in front of me, and we have some people who are on Adobe Connect. So I want to welcome everybody, physically present or virtually present. I'm doing this for the first time. We're live streaming this. I know that you know that. We're still kind of trying to figure out what's the best way to do it. But I'm sure we're going to find something that works. So welcome to Circuits. I know that this is summer, and maybe some of you would have preferred to do something else during the summer, but I know that most of you are very enthusiastic about taking circuits during the summer, so I applaud that, and I'm hoping we're going to have a good time together. So I'm going to be your instructor. This is my name right here. I'm Rafiq Gindi, and we are going to be having 3 TAs with us. 2 of them are actually right here. We have Faisal and Binbin. So they're going to be working with you for labs and tutorials, and also assisting me. Faisal is going to be assisting me here for Adobe Connect. And I can see already some people who are chatting. I have a chat window. I don't need to read that. Faisal, please, you take care of that, because otherwise it's going to be too distracting. Because some people are saying, I can't hear, oh, the sound is good. No, maybe you should try this. Or, you know, what are you doing this evening? So that's going to be too distracting. So Faisal is going to handle that part for me, and I'm going to be focusing on you. We have the presentation showing up here, and the doc cam on the other screen, so that when I'm solving some problems with you, you can follow on the doc cam, and this is all streamed, and I'm hoping that it's going to go fine. Okay, so this is my office. This is my office hours. So because you're already coming on Tuesday and Thursday, so I plan my office hour to be also on Tuesdays and Thursdays at 1:30 to 2:30. So I have an hour on each of these 2 days. This is the textbook I'm using, except that the picture shown here is the 5th edition. We now have the 6th edition, so it looks like that. Okay. And the description, basically, this is what the course should cover. This is my fleshing out of the catalog description based on the specifics that we're supposed to be covering this. So it's a course that explores the fundamentals of analysis. You're going to find that some of that stuff, I mean, or let me rephrase that. The way I'm doing it, I'm doing circuits from basic principles, circuits from fundamentals. You're going to find that that's what's in this textbook. That's what textbooks that good textbooks that are used in most big universities around the world. We take you from the builds and keep building. So we love circuit abstraction, circuit elements, LKV. If I ask you now, do you know KCL? I know you know it. Who knows KCL? Yes. Yeah, thank you. That's the title, but what is it?
Yeah, someone will argue. Yeah.
The sum current in equals current out. KV, Kirchhoff's voltage law. This one is trickier. Like KCL, Kirchhoff's voltage law, and Ohm's law. What's Ohm's law? What's Ohm's law? Any guesses? Yes. Voltage is equal to current times resistance. In a nutshell, that's what it is. That a voltage that depends on a current sum equals based on Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. That's the foundation. We're going to stay in this field on that. We're going to kind of develop. The idea, sorry, operational amplifier model, and then after rough elements, because for the first we're going to be looking at sources like voltage and at the end we're going to see how to in the system. The way I put it is that roughly I'm following for at least the first 8 chapters of the book. We're following the book very gently, about 1 to 3 and 4 methods of analysis and circuit theorems, week 5. It may not totally adhere to that. Sometimes I need some more time to cover something, so it may slip at the end a little bit for weeks, so we should basically just give it 1 week. And then we're going to see what happens later on. So this is really a tentative schedule, but it kind of captures most of what we're going to be doing. One important component, we have here the for labs and tutorials. And so we do, because we're not sure, are we right now in week 1? Put the actual dates. The schedule starting from next week, next Tuesday. You have annual labs on Tuesdays and Wednesdays. Okay, so some of you have them on Tuesdays, some have them on Wednesdays. For next week, going to have a lab or any tutorial. We won't have covered enough material for it, and the quiz, it's on CourseLink, so you're going to find it. I put up the instructions already, so you're going to follow that, and you have to pass that quiz before you are allowed into the week after that. So the week after that, May 23rd and 24th, that's what we call Lab 0. It's called Lab 0 because it's really introductory lab to know a few things about the equipment, about the power supply, the sources, the breadboard, the resistors, and also you get to know about some safety instructions. So as I mentioned, you have to have passed the safety quiz before you are allowed into Lab 0. Now, Lab 0 is not graded. You're not going to be asked to submit anything for Lab 0, but you have to attend Lab 0. Absolutely. Okay. And then tutorial. And starting June 6 and 7, we go on this schedule of 1 lab week and then 2 tutorial weeks. 1 lab week, 2 tutorial weeks. The lab is always due 1 week after you finish it. So for example, if you come on a Tuesday, then you are asked to submit your report on the following Tuesday. Okay? In the lab, you're going to see the TAs. They're going to tell you exactly how like what kind of lab to submit them and all of that. So that's the schedule. Now, I have a quick note, not quick really, but it's really an admonition about the tutorials. Circuits is not hard if you learn to do it all by yourselves from basic principles, okay? And I insist that you have to solve problems by yourself. If you don't take time to learn how to look at a circuit and then kind of think your way through the circuit and know which method you're going to adopt and how to solve using that method, if you just watch me doing it, or if you just watch somebody else doing it, or if you just look at the solutions, you think that you can do it because you can. But unless you do it yourself alone, you're not going to acquire that skill. Okay? So I'm going to say that. I'm going to say it again because I find people like all the way until the end, even after the midterm, coming and saying, like I'm having difficulty, I don't know what to do. And I'm asking them, do you solve by yourself? Do you take time? Do you spend time trying to solve those circuit problems by yourself? And that's the only way to learn circuits. Okay? Learning circuit is not going to come by looking at the solutions in the book. You have to do it yourself. Okay. The grading scheme. Labs count for 15%. And according to the previous schedule, the previous slide, we had Lab 0, which is not graded. Then you have Lab 1, 2, 3. So you have 3 labs. Each one counts for 5% of your final mark. And labs are a good way to get grades. And typically students get good grades for labs. So at least you have those 15%. You can count on having a good percentage of that. The midterm, I set it on Saturday, June 24th. And I decided I like to do the midterm at the end of week 6, after 6 weeks of work, so we have enough material. The midterm counts for 25% of the final grade. And I set it on a Saturday so that people who are on a work term, the ones who are right now following us on live streaming, that they can make it, they can come. The time is still going to be determined, but at least that's the tentative schedule that I put. Final exam is set on August 14th from 2:30 to 4:30, I think, so that's already decided. And I have 2 quizzes, quiz 1 and quiz 2. Now, each one of these quizzes counts for 5% of the final grade. I like to schedule quiz 1 around the end of week 3 and quiz 2 around the end of week 9. For 3 weeks, you have to wake up. And so that quiz is just kind of to get you into the mood of like testing yourself, seeing if you understand enough, if you're practicing enough. It's the kind of wake-up call. And it counts for 5%, so that's not too much, but that's enough to get you interested. The midterm is going to be covering everything that we do starting today all the way up to the week of the midterm. So it's kind of comprehensive for those 6 weeks. And then I schedule a second quiz, which is going to be hopefully by the end of week 9. So we're going to have like 3 additional weeks after the midterm. Quiz 2 focuses only on those 3 extra weeks. Okay, so it gives you a focus time to kind of study that part which came after the midterm. And then the final, after week 12, which is at the very end, is comprehensive. It's going to be covering everything. And I don't even have to mention the fact that it's comprehensive because, as I mentioned in circuits, everything builds on top of each other. You cannot possibly solve a problem from the second half of the course if you don't have everything really well covered for the first half of the course. So I had some people ask me in a previous iteration of this course, you know, is it going to be comprehensive? You have to know everything from the beginning or just, you know, like covering the second half. Obviously, there is a lot of material that needs to be covered in the second half, and the final tends to focus more on that. But you're going to find that you cannot solve that without really knowing very well everything that happened before the midterm. Okay? So it's going to be comprehensive in that sense. Okay. Any questions? Yes. The quizzes, well, I used to do that during the classes, but again, because of the way we're doing it and streaming and some students are not here, then I have to rethink that. I won't be able to have it during the class if people are not going to be able to come. Is it going to be in the evenings? Probably, but is Tuesday or Wednesday evening a good day to have that during a lab day or tutorial day? Again, I'm thinking about that. Maybe not. I'd rather have everybody together in one session instead of having people do a quiz on Tuesday, others do a quiz on Wednesday, and then, you know, discover that all quiz on here. Better to have everybody in together. So I may end up scheduling a separate time when everybody can quiz. It's just like it, but if we plan it right, I think we're going to avoid a lot of headache. Other questions? Okay. Office hours for TAs. I'm going to discuss it with the TAs. I haven't had a chance to discuss that with them yet, but as time goes by, we're going to post that and you're going to know when now, please email me, or if you email the TAs to say, you know, just to make sure that I'm available or that they are available. So even though I have my office hours posted and I'm encouraging you to come during those office hours, just knock on my door, I'm going to be there. Sometimes if you have, or if you're trying to contact all the TAs, email works well. Okay. All right, so I'm going to start. First, on the chat box to Faisal, and are able to follow that you're hearing the screen properly. I have this here, and actually, we could kind of see what shows up on the doc cam. But I was going to ask a question about that. What is this drawing? Okay, I'm just going to ask you to tell me what this is. You can, you know, for the people who are on the Adobe Connect, please just kind of type it and tell us what you think this is. Okay. Now, the lectures that I'm using, I am posting those slides on CourseLink. Did anybody see that? Okay. You're going to find that I tend to do that. I post them before the lecture. I post the whole chapter, and I'm encouraging you to print it and bring it with you. And you're going to find that many sections are, not many, but some parts are left blank. And the idea is that I'm just trying to help you take notes through that. So instead of you having just to copy everything that's on the slides or just trying to take notes and not really focusing, I'm sparing you some of that effort by giving you this. And then you're going to have to fill in whatever is missing. So this is the first chapter, basic concepts. You're starting here. So what is an electric circuit? An electric circuit is an interconnection of electrical elements. That's the definition that's in the book. It's a good definition. Sometimes I bring alternative. Because they are an electronic component in a sense. It's actually an extensive circuit which contains electronic components in it. But as a whole, as a building block, when we use the building block of what we call an operational amplifier, we tend to use it as not as an electronic circuit, but really just as one of the components that we have. It's a delightful little thing. You can do so many things with operational amplifiers, and we included it here. For some reason, I discovered that most electric circuits textbooks tend to have a chapter on op amps, operational amplifiers, even though it is an electronic component. So when you see that, I'm showing the textbook again. It says fundamentals of electric circuits. So you're going to find here all the circuits that you can build using the components that we're talking about, but you're not going to find in here diodes or transistors. Otherwise, it would be a textbook on electronic circuits. The International System of Units. These are the basic units that we have. We tend to like to start here. Units are very important to us. These are the basic units in the international system, which we call SI. And I guess you know what is SI. What does SI stand for? Why is it not IS? Yes. It is French. So what is it? What does it stand for? What's SI? Yeah, it's Système International. That's SI. We don't use IS, and thank God we don't use IS, because right now, you know, IS kind of means something different. Okay. So you have in this system, those basic units, you have 7 basic units. Meter for length, kilogram for mass, second for time, ampere for electric current. That's a basic unit. So if you have current measured in ampere, that's a basic unit. Meaning that it is not derived from the other basic units. Okay? You cannot define time, second, in terms of other units. You cannot say, oh, second is so many kilograms per meter. You cannot do that. Okay? So these are basic units. Ampere is one of these. It's the intensity of electric current. Okay? And then you have thermodynamic temperature, which is degree Kelvin, K, from which you derive the other units. For example, degree Celsius is just like a shift on the scale for degree Kelvin. Then the amount of substance, that's something that you use mostly in chemistry, mole, and light intensity, candela. So these are 7 units that are basic. You cannot define one of these units using the other units. For our study here, we are not going to be using all of these units. We are mostly going to need ampere, second, something in length, but not too many. Now these are the SI derived units, okay, and there are more than these, more common ones. Is measured in hertz. Now hertz is not a basic unit, it's a derived unit, because hertz is frequency. Frequency means something that repeats a certain number of times per second. So hertz means times per second. So it is a quantity per second. Per second means second to the minus 1. And that's why you can define hertz using one of the basic units, which is seconds. Force in Newton. Newton is kilogram times meter per second square. So you're going to find on the right-hand side of the slide all the basic units that make up the definition of your derived unit. Energy or work, joule is Newton meter. Power in watts, that's joule per second. And we're going to be needing many of these. So we're going to be using like frequency, energy, power, electric charge in coulomb. Coulomb is the unit that you use to measure charge, like you would say, what is the charge of an electron? Okay, anybody knows what's the charge of an electron? How much is it? No. Okay. Yes? Negative, yeah, 1.6 times 10 to the negative 19 what? Coulomb, exactly. Thank you. So this is the charge of the electron, and you're supposed to know that. Okay. Volts, that's joule per coulomb. Ohm, that's volt per ampere. Siemens, that's ampere per volt. Farad, Weber, Henry. So all of these are units that we're going to be using in our study of electric circuits and how they relate to the basic units. Prefixes. As engineers, we like to use what's called the engineering system. I think you probably have discovered that on your calculators. If you look at any modern calculator, you're going to find that you can have the exponent in terms of 3. So you can have 10 to the power 2, or 10 to the power 6, or 10 to the power 7, or 10 to the power 8. But if you use the engineering mode, it's always going to shift that to the nearest, one of these that you have here in that column. So if it's something that's kind of 10 to the power 3, we call that kilo. Kilo means 1,000 in Greek. If it's 10 to the power 6, it's mega. 10 to the power 9, it's giga. And then you go up, it's tera, peta, exa. And you are fortunate to be in a world where you kind of are familiar with these units, mostly because of the explosion of technology. Now you know what is a gigabyte, what's even a terabyte. When I was in your shoes, we did not have that. We kind of knew what a kilo was, because you buy a kilogram of fruit, but we did not yet at that moment in time think of what would be 10 to the power 6. So giga and tera and peta and exa are those multipliers. And then if you go into the much smaller, so 10 to the negative 3 is milli, we know this one, and then you have micro and nano and pico, and then femto and atto. Now femto, 10 to the negative 15, is a very, 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 very small quantity. And for those of you who are going to go further into designing electronic circuits or microchips or integrated circuits, doing microelectronics, you're going to find that you have like really incredibly small quantities of charge, not charge, of capacitance that exists between some wires on that very, very small scale, and we measure that capacitance in femtofarad. So femto is a useful unit, even though it is so small. I personally haven't had to deal with anything in the atto range, and who knows, maybe you're going to need that as well. But at least down to the femto, you're going to have to know what are all these prefixes. Okay, so if you have something that deals with, picofarad or nano seconds or whatever, you have to know what a nanosecond is. Okay, so this is an example, and I'm going to use the DocCam to solve that. So it says a signal can travel in a cable at 80% of the speed of light. So you have a signal, you have a wire, and the signal is traveling at 80% of the speed of light. Speed of light, we refer to that as c. And how much is the speed of light? Anybody knows that? Yes? Okay, 3 times 10 to the what? What's the, sorry? Meters per second, okay. So we have a signal that's propagating at that speed. What length of cable in inches represents 1 nanosecond? It means like after 1 nanosecond, where will it be? Okay, so it goes here and you have 1 nanosecond. So how far did it travel? Okay, so you have the formula that distance equals speed times time, right? So you want the distance, so the speed is 3 times 10 to the power 8 meters per second multiplied by, oh sorry, that's not the speed, that's and I'm just gonna have to do this like that. Okay, so what do we have? We have 3 times 4 times, how many zeros do we have left here? We have 10 to the 8 zeros, and then to the negative 9, so that's negative 1, and another one, so that's, right? And the unit that we still have here is meters. Okay? So how many centimeters is that? One meter is 100 centimeters, right? So instead of writing meter, you have 100 centimeters, because I want it in centimeters to do the conversion into inches. So that's really equal to 24 centimeters. How much is that in inches? Now 1 centimeter is equal to how many inches? Yes.
0.25.
But 1 inch is equal to 2.54 centimeters. That's correct. So 1 over 2.54, and now we have that in inches, right? So how much is that? 2.4 divided by 2.54. Sorry, not 24, I mean, divided by 2.54. Anybody has a calculator? Nine? Couldn't be 9. Oh, wait, no, it could be. Sorry, you're right. Again, 9.44 inches. Is that what you're getting? Okay. So the point here is just a very simple equation like that. And then when you're using the units, you have to know how to convert from one unit to the other. Okay. We're looking now at some concepts. We have here the concept of it's not easy, because sometimes there are things that, you know, they're not very, they're obvious, you understand them, but you don't really have a good way to describe them. So this definition says that electric charge is the basis for describing all electrical phenomena. Now that really tells us anything about what electric charge is, but we're going to look at it here. Charge is an electrical property of the atomic particles of which matter consists. Okay? And charge is measured in coulombs. It's just telling us that charge really comes from the properties of atomic particles. We know that electric charge exists in discrete quantities, and you cannot have a charge that is not an integral multiple of the basic quantity, the electronic charge, which is 1.6 times 10 to the negative 19 coulombs. So any electric charge anywhere in the physical world has to be an integral multiple of that. You cannot have a charge that is half of that, or a portion or a fraction of that. Now, the separation of charge creates an electric force, which we call voltage, and the motion of charge creates an electric fluid, which we call current. Now, I like to explain that by making a demonstration. I'm just thinking how I can do that for people who are watching us on Adobe Connect. I'm going to make the demonstration. Okay, I know what I'm going to do. I need 3 volunteers, please. Yes, please come. Yes. I'll tell you what, I'm gonna have 4 volunteers. I need 2 guys and 2 girls. So I need two girl volunteers, please. Anybody? Yes. Thank you. What? Come. Yes. Thank you. Okay. So it's a good thing we have a camera so people can see you. I'm going to use one, positive charge. You are the positive charges. You are the negative charges. All right. Just gonna put you. I want the camera to see you. Everybody, just go a little bit on the side, please. And just, what's your name?
Abdullah.
Abdullah is going to be my positive charge. So you stand here, okay? All right. Can you see him on screen?
Abdullah.
Okay, so this is Abdullah. Thank you. You're a positive charge, remember? Okay. And you are? Laura. You stand here, please. Yeah, so you are a negative charge. Okay? All right. So what happens when you have positive and negative? Yeah, I'm gonna say you cannot. I guess I should be here so that people can hear me. I hope you can hear me. So we have Abdullah and Laura. They are fixed charges. They cannot move. But because we created what we call a separation of charges, we put some positive charges somewhere and some negative charges somewhere. Created of, and then, okay. Let's read that again. The of charge creates an electric force. Okay. So if we have a lot of Abdullahs here and Lauras, there we have the strong voltage. You cannot move, but they have created that. That's what, at a separate distance, at a specific distance. I'm going to introduce another positive charge. What's your Brandon? Brandon is another point. Abdullah and Laura, that attraction, that voltage creates an electric field. You know what's an electric field? Okay, so electric field, we draw that in terms of like a field that's going from A to point B. Electric field goes from the positive charge, Abdullah, to the negative charge, Laura. So we have electric field flowing in that direction. Okay, now here the electric field. You are slightly so we can see you. Thank you. Now, so you're going to introduce it at Abdullah's point. Move you, right? Go into the field. Go in like that, yeah? And then what happens to you? You are by Abdullah and you're attracted towards Laura, okay? So you are a moving charge, current, okay? All right. So you move out of the other moving current, the other negative charge. You are Dima. Dima, step into in the middle. Now, Dima is a negative charge. She is in the same electric field. She's under the influence of that same voltage, okay? Now, what's going to happen between you and Laura? Repel. What's going to happen between you and Abdullah? Attract, okay? So you're going to move in this way because she can move, all right? Okay, so thank you. Dima, you can move out now. So this is what really happens at the atomic level, or like inside a wire or stuff like that. You have at one end somewhere a fixed positive charge and somewhere else a fixed negative charge. These charges, they cannot move, but they create an electric field. And because of the electric field, we have this force, and that force is called a voltage. Now, if inside that field you have a moving charge, a charge that can move, whether positive or negative, it's going to move according to its polarity. Okay? So these are voltage, and they create the current, because current is because of the moving charges. Okay? Thank you. You can go now. So my point here is this. A voltage is fixed. Voltage does not move. Voltage does not flow. Okay? Voltage exists because of some conditions that have created that separation of charges. So once that condition exists, it is there, and we have to know where is the positive charge, where is the negative charge, or we're going to see how to deal with, like those voltages according to KVL. However, a current does move. A current is a flow of charges. Okay? And whenever you have any charge that moves, automatically you have current. We're going to see the definitions of that. So first here we have another problem. How much charge is represented by 4,600 electrons? Okay, that should be easy because you just multiply that by the charge of one electron, right? Okay, and that should give you. Yeah, I can't really see. Yeah. Okay. So this is the amount of charge that you would get if you had 4,600 electrons. Okay. So you just do that with a calculator, whatever it is, and that would be in coulombs. Okay. But you have to understand something. Electrons carry a negative charge. Okay, so whatever number you're getting, you know that is negative because these are. Now I said how much charge is carried by 4,600 protons. It would be the same value, but it would be a positive charge. Okay. Definition of current. As I just mentioned, current comes from moving charges. So an electric current is defined as the rate of change or the time rate of change of charge. Measured in amperes. Okay? So the flow of charge, the rate of change of in amperes, that gives you the current. And you have the definition, I by definition is equal to dq dt. Okay? It's the rate of change of charge with time. So again, if you look at that, the definition would be 1 ampere is basically 1 coulomb per second. Okay? At this other blue box, because now once you know this first definition that I is equal to dq dt, then you can see that the charge Q is the integral, right? Of I with time. Q equals infinity. To another time, it's the amount of charge that you would have. Now, what is this charge? It's when you have a current that is flowing and you know how much charge past a certain point. So it's okay, I'm going to count from time t naught up till the time t, just the charge went beyond a certain point, and that's to do that. Now, current comes in different flavors. So first you have a DC current or a direct current. It's funny because the word DC means direct current. And you're going to look at DC voltages, which are voltages, but we still call them DC, so it's direct current voltage. It's a bit of a misnomer. But the direct current is a current that remains constant with time. So I would say, if the flow of charge is constant, which means I get always, like 10 coulombs of charge flowing per second. Charge is flowing at 10 coulombs per second, 10 coulombs per second. So that tells me I have a fixed current of 10 amps, 10 amperes. Okay? So that's called a DC current. And you can also have what we call an alternating current. and AC, and this is a just sine. Now look at that. You have the time on the horizontal axis, and the vertical axis has the magnitude of that current. So if you look at that, it's not like the current is going in a ripple or has convulsions or anything like that. What's really happening is that the current starts at some point, the value of current is 0. Charge is not moving. And then as time goes by, you find that the intensity of current is increasing, means that charge are moving, and they're moving at a higher pace, higher rates. So you have more and more current until you reach a maximum, which is the peak of your amplitude. And then the current starts to slow down, meaning that the charge is flowing at a slower pace until it goes down to 0 again. And then look what happens. The current now is flowing at a negative rate, meaning that the rate of flow of charge turned negative. So if charge was first flowing, going into a wire from A to B, now it's going to go from B to A. So it's the alternative. The horizontal axis means the current is positive, and when it goes below, it means it's negative in certain directions. So the current keeps going back and forth, it increases in intensity, it reaches a peak, it goes lower in intensity, it changes direction, it goes in the opposite direction, and so forth. Now, typically, we use those symbols to describe current. The letter is I. When it's a DC current, you use a capital I. When it's an current, you use a small I. Okay, so that's the convention that I guess everybody agreed upon, and this is what you're going to find in most textbooks. Now, we said that current is represented by flow. So the current flows through an element or a wire in a given direction. So you have to tell me what is the assumed direction of your current. So here, I'm assuming that these are direct currents, DC currents. So look at this red wire, and you have this current flowing according to that arrow through that element or through that wire. So if I say I have 5 amps flowing in that direction, mathematically, it's exactly equivalent to saying I have negative 5 amps flowing in the opposite direction. Okay? So here, the direction and the polarity, if you will, okay, if it's positive or negative, are tightly related. Okay, and we're gonna play with that a lot. We're gonna say, okay, if I have a circuit and I have a certain current flowing in a particular direction, for example, if you have a wire like that, I have here a current of 5 amps. But exactly like I'm saying over there, I could say this is exactly the same as having a current like that that's equal to negative 5 amps. And that is going to, because usually we don't know in a circuit how much current there is. So you do that and you say, I have a current here of I1. And I1 is going to go into an equation, you're going to solve for I1. So if I1 is positive, what does that mean? Okay. If you solve and you find that, and you end up with I1 equal positive or plus 9 amps, it means that it is flowing in the direction that you had assumed, okay, along that arrow. But if you solve a problem and you assume that you have a current like that, I1, and then you solve and you find I1 is equal to, like say, negative 3 amps, it tells you that the current is effectively flowing from the one that you assumed. Okay? So this is a mathematical representation. You can have positive currents, negative currents, but that all depends on the assumed direction. It depends on the arrow that exists in your assumption. Any questions here? Example, the total charge entering a terminal. We're talking a terminal here, we're talking about an electric, a point in an electric circuit. And this is given by Q is equal to this. So you have this equation Q equals 5 sine 4 pi t in millicoulombs. So please be careful with the milli here. We want to know the current at t equals 0.5. Seconds. Okay? So the current I equals dq dt. Is it showing okay?
Yeah.
I is equal to dq dt. So it's d by dt 5 sine 4 pi t, right? But remember, this is in millicoulombs. We're going to get a result in milliamps. So how much is that? 5, and then the derivative of the sine.
Isn't there a t metric? It's like Q equals 5t sine.
Is it? Yeah, you're right. Sorry. Oh, okay. So that's our 5t sine. All right. Thank you. So that's equal to, okay, the 5 stays out anyway. So I have sine 4 pi t plus t multiplied, thank you, t multiplied by cosine 4 pi t, and then you also have a 4 pi here, right? So how much is that? Five sine 4 pi t plus 4 pi t cosine 4 pi t. And we want to use t equals 0.5 seconds, right? And here. Sine 2 pi plus 2 pi cosine 2 pi. And all of that is in milliamps. What is sine 2 pi?
So really cool. It's because it's a charge equation, so it should be.
No, this is current.
Oh, sorry.
Current is dq dt. Okay. So this is going to be a current. And because I had a millicoulomb here, okay, so I'm ending with milliamps. What is sine 2 pi?
0.
It's 0. So that is 0 plus. What is cosine 2 pi? So this is 0 and this is 1. And I have a 5 times 2 pi, so that's 10 pi in milliamps. Okay? Okay, another example. Determine the total charge entering a terminal between t equals 1 second and t equals 2 seconds if the current passing the terminal is, and you have a current equation. So now we have to integrate. I is equal to 3t squared minus t in amps. Q, you have to integrate between t equals 1 second and t equals 2 seconds. Okay, because q is I dt, so that's what we get. So here we have 3t squared is t cubed minus t squared over 2, and the limits are going to be 1 and 2. Equals 2 minus 1 half, let's do the 2 first. 2 minus, sorry, 2 cubed, let's start that again. 2 cubed minus 2 squared over 2 minus 1 cubed minus 1 squared over 2. Okay? 8 minus 4 over 2, and you have 1 minus 1 half. 8 minus 2 minus 1 half, right? So it's 5.5 coulombs. Okay. Okay. So we looked at what is the definition of charge. Current is the rate of change of charge. I equals dq dt. Now let's look at voltage. What's the definition of voltage? Voltage is also called potential difference. Okay? It is the energy required to move a unit charge through an element. So voltage here, we already discussed the fact that voltage results from the separation of charges and keeping charge fixed at a distance from each other. Voltage comes because there is this attraction between positive and negative charges that gives rise to an electric field. But now, when we want to define the value of voltage, we use the concept of energy, because voltage is related to energy. How much energy do you need to move a unit charge through 2 points, which are those fixed points that you have? So by definition, VAB, the voltage between those two nodes A and B, is by definition dW dQ, which means that 1 volt is defined as 1 joule per coulomb. Okay? Now this is really the definition in terms of physics or in terms of fundamental units. When we're working with voltage, we are going to develop some more useful ways to understand how to deal with the voltage in a circuit. Okay. The front row here, I'm sorry, just the way it is set up, you're having difficulty, so maybe you may want to sit more towards this side next time, okay? Because, I mean, the way we're doing it, I don't think we're going to be able to change much, all right? So just can't move a lot here. Okay, so the voltage or a potential difference is always measured across an element, okay? So when we say an element, you see this yellow rectangle that you have. I'm going to say this is a circuit element. We don't really know what it is, what's inside. It could be a resistance, could be a source, could be anything. But we say that if you have any element as being the voltage across that element. Remember, the current flows through the element. Current is a movement or a flow of charge. It moves through the element. Current, that's the current. The voltage does not move. So the voltage is always defined as how much voltage or potential difference you have between 2 points or across a certain element which means the 2 points that are across from there. Now again, you have a polarity here. So if you look at the first drawing on the left, you have those 2 points A and B, and we call that VAB. When I say VAB, look at the suffixes here, A and then B. VAB means how much VA is at a higher energy level than VB. VAB in this case is equal to 9 volts. So you always have a polarity because we want to make it very clear when we're saying the voltage is the potential difference between two nodes. So I'm talking about difference between two nodes. I want to say, okay, we're talking about how much this node is higher than the other one, or is it the other one higher than this one? Okay, so I have to have a polarity. So we're going to put a polarity with a plus and a minus sign. So you have it like that. VAB, so you put the plus at the A and the minus at the B. In this case, it's equal to 9 volts. And that is equivalent to having VBA equals to negative 9 volts. So again, like, if you switch polarities, you can use a negative number here. And I'm going to illustrate that here like I did for the current. Sometimes you have a circuit. You can have many elements in that circuit. Okay. And I want to know what is the voltage here. I'm going to call that Vx. So I put the polarity plus and minus, right? Now I'm going to use that, and then using equations like KVL, I'm going to have some equations, I'm going to solve that, and this is an unknown, I'm going to solve it, and I'm going to end up having a value. Okay, so let's say you solve and you found that value for Vx equals 10 volts. Okay, it tells you that 10 volts is going to be the voltage or the potential difference like that, meaning this node here, or this side of your element, is at a higher energy level than this side by 10 volts. Okay, so what if, you do the same thing for that and you say, I'm going to solve for Vy. And then after you solve those equations, you end up having Vy is equal to negative 6 volts. Okay, so what does negative 6 mean? It means that either you keep that like it is and you say, oh, it's like this is negative 6 volts, meaning that the top node is at an energy level higher than the bottom node by negative 6, or you could say it's equivalent to saying it's like that. Okay? It's in fact the bottom node is at an energy level which is higher than the top node by positive 6. Okay? So I'm going to find those situations occurring all the time where you have a certain polarity, plus or minus, and with the voltage you have to have a polarity. And then you discover what the actual value is. If the value that you solved for, you end up getting a value that is positive, it means it is according to the polarity that you put. Like you have it on the screen here. 9 volts, that's VAB. If you end up having a negative value, it means that the polarity is in fact flipped. So that would be a negative 9 volts becoming a positive 9 volts if you flip the polarity that you assumed. So remember, a voltage is always measured according to a certain polarity, and a current is always measured to flow according to a certain direction. Okay. And from here, you can get this, which is an obvious fact, that VAB is equal to minus VBA. Okay? Yes?
You show me what to resolve.
Sorry. Solve that. I said if you solved and you ended up if you solve and you end up having Vy being a negative 6 volts, it means according to what I, the plus and minus Vy equals negative 6, or you can decide, oh, that means that I can flip those two polarity and I have a plus 6. Okay? Any other questions? Okay. Now with voltage and a circuit, the box they have on top represents any element that you may have in any electric circuit. So we represent that by, I mean, it could be this rectangle thing, okay? So rectangle has two terminals. In this case, they are 1 and 2, which are the two sides of your element. So for example, if this is a resistance, it has two ends, right? So it's going to have two terminals. In this drawing, they're called 1 and 2. So you always have to show me where is the assumed direction of flow of current. So in this case, I flows through the element from 1 to 2. You see that? Okay, that going through your element terminal, that's the assumed direction. And you're assuming that the voltage V into this polarity of a plus and a minus, and you're assuming that the voltage at node 1 is higher than the voltage at node 2, or the voltage difference is according to this polarity. And we're going to see how we do that when we're solving problems. When we're solving problems, we kind of go around the circuit. It's like kind of like walking on the circuit. So let's look at the circuit that I have drawn here. Okay, let's say this is a circuit here. I'm gonna look at V1. Look at the voltage here. It has a known polarity that we just assumed right now. And as we're going around a loop, we're going to see what that means. But with KVL, we're going to be doing that all the time. If I'm walking, let's say, like this, and I'm going like that, and then I'm following through that element from the top part to the bottom part. See, I'm moving in that direction. I'm moving from the plus sign to the minus sign. It means that I'm moving from a node that is assumed at a higher potential, a higher energy level, to a node that is at a lower energy level. We call that direction a voltage drop. Okay? Now somebody else will look at that circuit and decide to look at it in a different way. They're going to say, oh, no, you know what? I want to move in the opposite direction. I want to follow my circuit and I want to go like that. Okay? I want to go as I'm moving in this direction. So if you're doing that and you're moving along the circuit, and we're going to see how we do that with KVL, probably next week, you're moving from a node which is at a lower energy level to a node that is at a higher energy level. We call that movement a voltage rise. Okay? So, voltage rise and voltage drop are two sides of the same coin, because it's the same element with the same polarities. It didn't change anything. It's just how I'm looking at it. If I'm looking at my elements by trying to go from the higher energy level to the lower energy level, we say we are experiencing a voltage drop. But if you're going through the circuit from a node which is at a lower energy level to a node that's at a higher energy level, we call that a voltage rise. Because in circuits, the current can actually flow in any direction. So sometimes the current can flow inside your element in the direction of a voltage drop. And sometimes the current can flow in your element in the direction of a voltage rise. So my question is, if you look at the circuit that's on the screen right now, which direction is the current flowing inside your circuit through? Is the current flowing in the direction of voltage rise or a voltage drop? It's a voltage drop, okay? Because we have determined that node 1 is at a higher potential than node 2, which means that the current is now flowing inside your element in the direction of a voltage drop. In some other cases, you can have a current flowing in the other direction. We're going to say the current is flowing in the direction of a voltage rise, okay? So here we have defined voltage drop, voltage rise. And again, what it just says here, when you're looking at the current flowing into the terminal 1, it means there is positive charge flowing inside your element, because current is always the direction of a positive charge flow. Okay? So we're saying that we have positive charge flowing inside the element from node 1 to node 2. Or it means that you have negative charge flowing in the opposite direction. And the importance of that is because in real circuits, in real life, most of the current is carried by electrons. Electrons are negative charges. So if you have a current flowing in a certain direction, it means physically that there are electrons flowing in the opposite direction. You don't really have to worry about electrons all that much. This is mostly like physics, because most of the time we're not thinking in terms of electrons. We're thinking in terms of current flowing, regardless if there are electrons or something else. Okay, so I'm stopping here. Thank you very much. I'll see you on Tuesday morning.
I'm considering taking this course in the summer.
Yes.
I think it's not my degree requirement. I'm thinking of taking it.
It's not a potential degree, you're saying?
Yeah, but the thing is, I will probably require your signature on that course. So my question was that, I mean, I don't have the pen today with me, so are you going to be on the campus on Friday or on Monday? For sure.
Maybe on Monday, I'm not sure yet. How do you stop it? I'm not sure yet. Because I was just discussing some stuff that maybe I need to do on Monday. But tomorrow I'm not here. And I don't know about Monday. You may only start maybe on Monday.
But maybe
we could do it before the class on Tuesday.
Okay, but the thing is that it will be past deadline, but I think it's okay to do that. So it will be late on Tuesday.
Do you have it today on the now?